Welcome to this presentation about hardware abstraction layers. My name is Francois Normandin and I'm a certified LabVIEW architect. I'm working for JKI. JKI is a San Francisco Bay Area systems and software consulting company. We specialize in a broad range of services, from instrumentation of R&D and large-scale systems, to embedded software development, including FPGA, to web, mobile, and cloud technologies. As part of this presentation, I'm going to first define what is an hardware abstraction layer, why it's useful when designing systems, some pitfalls to avoid, typical architecture for hardware abstraction layers, including some UML representations. Finally, I'm going to build a Microscope app with LabVIEW in order to demonstrate how to implement an hardware abstraction layers. For that, I'm going to use state machine objects. What is a hardware abstraction layer? It's a software architecture which provides a device-independent interface to physical hardware. Its main purpose is to conceal different hardware architectures or implementations and provide a uniform programmatic interface. Some examples of hardware abstraction include general concepts like a multimeter, or pump, or camera, or an axis. These very generic categories of instruments allow us to define a generic interface, such as start and stop, or measure, or grab image. Through the use of an hardware abstraction, we can then support multiple instruments of the same kind, and we can reuse different components into the same application. This leads us to why is it useful to use an hardware abstraction. First, it allows applications to access a common set of functionalities with little knowledge of the actual hardware implementation by virtue of communicating with hardware components in a generic way. It facilitates portability between different deployment targets or OSs. Think about compact RIOs for your proof of concept and then migrate to a system on module or custom microprocessor-driven board. Also promotes software engineering best practices through code reuse. For example, parts of your hardware abstraction will be useful in test systems, others in manufacturing, QA and QC validation, engineering tools, and most likely in the final product itself. It's unit testable, and it's highly maintainable. And we'll see in the demo a concrete example of maintainability. It also mitigates risk associated with equipment failures, hardware obsolescence, like discontinued parts or components, supply chain problems. For those in a regulated environment, it also lowers recertification costs by limiting the scope of tests to compliance for changing one component. And finally, it allows system, subsystems, and component response simulation. Although an hardware abstraction is generally a good idea, there are some pitfalls to avoid, like developing an hardware abstraction architecture for a single component rarely makes sense. It's time-consuming, adds little business value. Mixing low-level and high-level functionalities increases the chance that future hardware won't fit in that nice little box that you've designed. Managing data in the abstract implementation, or trying to make an HAL too generic on the first iteration. HALs are not meant to be universal. If you find that your hardware abstraction doesn't fit your need, just duplicate the hierarchy and start fresh. For example, if we were to start with a sensor, a line CCD, and a scientific camera, they could all be considered digitizers, but it makes little sense from an API perspective. Let's take the example of a microscope. At high level, it can be broken down into two subsystems, an XY stage and a camera. Expanding a bit more on that representation, let's explore how our subsystems can be broken down. Both the camera and the XY stage should act here as a generic interface to whatever type of camera or XY stage that we will face in the future. So it's really important at that point that we will define an interface that makes sense. Here we're expanding with different types of cameras and type of XY stage, each one will call a different driver. In that representation, we can see that the camera can be of 3 flavors. It can be an IDC compliant camera, it can be a USB 3 camera, it can be an iMac DX camera. Each of these specific implementation of a camera will call a different driver. Same thing for the XY stage. To properly decouple our application and instrument drivers, we've just created an hardware abstraction layer. First, the application separation layer, which consists of abstract classes that provide a generic interface to the application. Second, the device separation layer, which implements specific functionalities and call the hardware directly through the driver. And now it's time for a demo where I'm going to use state machine objects as an underlying framework. As part of this demo, we're going to build a microscope, and let's pretend that we've got some requirements that require us to envision using a HAL, developing a hardware abstraction layer. For example, we've been instructed to build an instrument that will feature flexible hardware configuration, because already we've got to support multiple cameras in the lab, and we have 2 types of motorized stages for the microscope. So in the future, we want to be able to substitute hardware to achieve our objectives of performance improvement, cost reduction, but also we have different setups in R&D and manufacturing or production. We also have some hard requirements. At first, we need to use a certain specific camera, and for the purpose of this demo, I'll be just using my laptop camera, which I can control using iMac DX driver. One of our goals will be to create very modular components so that we can test early and deploy. Let's start by creating a new project. And for this, let's call this L demo. So the first thing I'd like to do is build a camera subsystem. So we're back with our UML diagram, which I've expanded with all the public functions that are going to be needed to implement our microscope. So as you can see, I've detailed the camera with the public method snap image, get image as pixmap, save image or save to file, and I've also added some callbacks for events on new image and image saved. Same thing for the XY stage, where we're gonna have to set velocity, acceleration, move, all the usual stage or axis type of functions. At higher level, our microscope will need to initialize jog to certain positions by calling the XY stage, get the stage position or get a camera image directly from calling the camera, but then also some composite functions like capture image at position, where it's going to do like capture image at position, where it's going to call successively the XY stage, and then when the move is complete, we'll snap an image, get the image from the buffer, and wait for the image to be retrieved. And obviously save image at coordinates or at well in the case where I've got a well plate installed on my microscope. But those are features that both will call the camera and the XY stage. I already prepared a LDemo empty project to proceed. So the first thing I'll do is I'll use our GKI State Machine Object Editor. Now, because this is not a State Machine Objects webinar, I'm going to go over this very quickly so that we stay on topic. Basically, I'm going to create a new camera subsystem. So create SMO. I'm already set up to go to the right folder destination, and it's going to be adding this camera class, which is my abstract class, to the project. I'm also going to add up right away the XY stage and the microscope classes. Now these three subsystems now mimic our UML diagram so far, so where we have basically the microscope, which represents our application, and the camera and XY stage abstract classes are our application separation layer. We will postpone for now the development of any device separation layer, more specific classes such as the camera.imacdx that we're going to do later on, and we're going to focus on going and preparing our public API, what will be the application facing interface. To do so, I'm going to take as an example the camera. And going to the API, I know that the API of the camera will have, like we discussed earlier, a get image as pixmap, or save image, for example. So again, using the editor window, we can go and add a public method that will get image. And at this point, I kind of expect that my images will be stored in buffers. So my buffer, for example, here is the only argument that I'm going to need. So as you can see, my get image has been created. And one thing that I personally prefer is to remove the namespacing from the public API and keep namespacing only for those methods that might interfere with the parent. But get image, the parent of camera, is just an instrument that doesn't get image, so I think I'm safe naming it get image. Okay, at this point, I fast forwarded to continue basically with the camera API, microscope, and XY stage APIs. So as you can see, I've completed get image as pixmap, snap image, save images, and I've also added the public events for new image and image saved. So I'm going to go into it just to show you what it looks like. So the get image will get the image as an image data, and I will provide a buffer number. Inside, I'm wrapping a protected method, which I've put into methods here. And this one is getBuffer. GetBuffer will be the method that we will override in the device separation layer to provide direct functionality, direct call to the drivers. In this case, you notice that a more generic call for a buffer is, in this case, instead of an image data, it's to have a pixmap. So my public function will just translate the pixmap to image data to provide the public-facing data type that a developer might find useful. And I've done the same for save image, for example, where in this case, save image will send a message to the process, and the process on reception of, save which buffer, probably the latest, with a path will do the work and fire an event that is image saved. So anyone that is listening to these public event here will know that an image has been saved at a certain path. I'm going to open the process. So the process is essentially the actor of the state machine object. It will receive commands through events, in this case snap image or save an image, and it's going to perform an action. So going through the process makes sure that we can serialize actions and make them asynchronously, so we don't have to wait for the image to be saved on disk, which might take time. The API basically through the user interface will not be blocking in this case. So same thing for a snap image. We will receive a snap image function, call the action to actually snap the image, get the buffer, and fire an event to say that, yes, we've got a new image at this point. What are the specific functions that a more specific camera will need to perform. Well, it's going to need to initialize and uninitialize. It's going to need to capture an image. It's going to need to retrieve an image from the buffer, and it's going to need to save an image to disk. So these are the basic under the hood functions that are being called by my public API. And just to prove that this is really an abstract class, I can open, all of these. They are all the same. And essentially a get image, because it's a direct call from buffer, which means that it's probably going to be non-blocking. You can call directly the get buffer method here instead of sending a request to the process to do something serially. Now, for expediency, I've done exactly the same here for the stage. As you can see, the stage has much more methods. We had seen that already in the UML diagram, where we can get the target position, get the real position, and I've also added in here, just for the sake of the demonstration, but a configuration where we have the real world units, which would be, for example, meters or millimeters, and the number of counts per unit. So this is a double value, meaning that it can be fractional. Among other utilities that I've implemented are list name position or store position. Essentially a way to set a position by name and store some units, some coordinates. And that maps well with move to a name position, where instead of providing directly a move absolute with the coordinates, we would give a name position, retrieve it from configuration, and if it exists, then do a move absolute. Okay, let's sort a bit our project in concepts. We know that our application will be the microscope, and we have our application separation layer that is ready here. I might as well take this opportunity to show the API for the microscope, and let's go with a capture image at position. As you can see, I've separated this as a synchronous call and asynchronous call. The only difference is that the asynchronous call goes through the process. So for this demo, I thought that maybe it would be simpler if we just called it directly, which obviously for instruments I would not be tempted to do unless it's really for testing in this case. But as you can see, our microscope has the real difference is that we've got dependencies on camera and X, Y stage, as we saw in our UML diagram. These are the references to both our subsystems. A capture image at coordinates requires us to move to those coordinates and wait for the move to be complete. So that means that even if this move here is asynchronous, like in this case, it is not. It's a synchronous call. But if it had been asynchronous, we could have waited for the move to be complete. And this is just a scheme here to subtract the timeout, to divide it between the stage moving and the camera timeout. So again, we capture the image. When we have the buffer, we can say that the capture has been complete and return the buffer value. Once our microscope knows that we have acquired successfully, then we would call the get camera image with that same buffer number and retrieve here our image data at coordinates. A bit of the same has been done for saving an image. In this case, we already have the image, so the microscope can directly save to disk using its own API instead of relying on the camera's functionality. Now, before we move to the device separation layer and building our first specific object, I'd like to retrieve a bit of a VI that is being created when we create a subsystem from the editor. There's always a test launcher that is being called, and in this case I've already added the public API to it. So as you can guess, I'll have a simulated stage later on, so you'll excuse me if I've already prepared it. But essentially, if we call the XY stage, and I'll show this class, this is really our class here that we've already explored. The goal is that any VI that is not part of the class will only be able to call the public API to that class, and that provides us with a kind of a playground to make sure that our class works the way it's supposed to. So one particularity with the XY stage that I haven't mentioned before is that as part of the private data, I've added the coordinates in both coordinates in real world unit and in counts, and by doing so I can very easily simulate a position, because in the degenerate sense, when there's no actual motion, if we assume that the motion is completed, we can just read what is the target position and substitute it for the real position, and that gives us a very, very quick way to assess if our logic for a positioner would work. For example, move absolute position would set those target coordinates, and then when we say read position, we would read the target. Therefore, we're already arrived at our destination. So this is a trick for simulating objects, real world objects, that I use very often. So in this case, let me go through that diagram here. So at first we and I'll just forget about the actual simulated stage for now and have our real stage. We create the state machine object, and that's really just creating the references. Then I'm setting the number of counts per millimeter in the configuration. I'm then looking for the public event to know when the state machine object will stop, start, or change state. And I've got my own XY stage public events, which I'll be listening to, and these public events are the ones that we've defined as part of our public events here, which are move complete, new position, I've updated the name position, and the move has started, true or false. So at that point, I'll be listening to all these events, and I can show it here. So whenever there's a new position, I'm going to display them and convert them to counts as well. When the move is complete, yeah, I'll say that it's complete. And when the move is started, I'll just say that the move is not complete. Essentially, that's going to tell me, with these being indicators and these here exercising my public API, where I can use move to absolute position, create a, move to a certain name position. I can also move some to relative. So then we move on. The rest of our test launcher is really just starting the state machine object, which is kind of launching the process asynchronously in a sense. And at the end, because when I'm gonna get that the state is stopped, then I'm gonna destroy the object. Oh, and by the way, how do we stop the object? That's because I've got a value change event for stop or I've decided to close the VI. So I think I'm ready to launch this little tester. So if I say that I want to go to 5.5 and move, then as expected, we're already there. We move home, it goes back to 0, move relative, and we see that it works. All right. Another thing is if we say 0, 0 is called base, and 0, 10 is called position A, then we could say move here, move there. So this little test launcher has shown us basically that our base class responds just the way it's supposed to. Now we should do exactly that same test launcher, but with whatever classes we come up with, whether we're connected to real hardware or we have a simulated stage that actually does some real-time simulation of, for example, acceleration, velocity, and things like that, to see if all our timeouts and our asynchronicity works correctly. Now, for a camera, obviously, there's no such thing like a target position and retrieve it to read the actual position. So we actually need to use images. So the first thing that I'll do is that we're going to create a camera.imacdx so that we can use the my laptop camera and see if we can make the same XY stage test launcher into a camera.test launcher, which works. Okay, so we are ready to create our first device separation layer object, which will be our camera.imacdx. Put that into the DSL here, and again, using the SMO editor, you would create a camera.imacdx. I've already created that so that it's going to be a bit faster. And because this is a more specific camera, all we need to do really is to override these 5 VIs that would not be created by the template. So you'd have to select VI for override, and here you would select all those that are relevant. In this case, camera.init, camera.oninit, and etc. So the first thing, as part of my iMacDX, I need to create references. So to initialize a iMacDX camera, we'll be calling directly the driver, and one particularity is that you need also an iMac container for the image. So in this case, I'll just create a generic, U32 RGB. In this case, I'll just create an RGB container because my camera is an RGB camera. However, if you wanted to make that more generic for your use, you might want to add a bit more logic here and insert maybe an image class that contains whatever type of image your camera is actually configured to produce. In this case, I went pretty straightforward. So again, that goes into our discussions about the pitfalls of an hardware abstraction layer. If you want to spend time upfront and cover all the different use cases where, hey, this is a camera that can do any type of images, any type of outputs, any resolution, 14 bits, 16-bit cameras, 8-bit cameras, color cameras, infrared cameras, whatnot. That seems like an overkill. You might be better off doing, a color camera abstraction or a 16-bit scientific camera abstraction, something like that. Anyway, you'll figure that part for your own application. In this case, I've simply overwritten capturing the image, and again, that is just an accessor to get my references, and I just drop the nodes. So very, very simple to get to create that iMac DX specific camera. So you can see I know that I need to match with my PixMap, which I had chosen early on as my main format to retrieve from buffer. So I've got a buffer number here. I take my image and I convert it directly to pixel, and that's going to map nicely. Now, one thing from using the base class that I didn't show before, but I had created a simple save image where if anything can be saved to, you know, PNG, JPEG, or bitmap from an image data, then I would do it. And otherwise, well, I'd say this extension is not supported. So I decided to support one extra type here, because iMac includes also saving to TIFFs. So because bitmaps, JPEG, and PNGs were already supported by the base class, if there were an error saying that it's not supported, then I would check here if we either stand with our error message because we cannot override for that format, or hey, that's a good news, we can provide, you know, an extra functionality here. So we'll clear the error and just retrieve the buffer and go straight to TIFF from iMac. That's one of those pleasant things with objects. I've also made a camera that's simulated previously, and the purpose of this is just to show how easy it is to swap between two specific types. So our camera simulated, all it does really is that instead of capturing an image, it captures it from a buffer. And so I've created a circular buffer as part of my dependencies. Circular buffer is configured to retrieve images from disk, and basically my buffer number becomes my index to retrieve that image. So I get the image, I have a new element index, and I fire the buffer. So get buffer is exactly the same thing, where from my circular buffer, if I've got an image, I get it by index and I publish to PixMap. That's it. Very simple. And I promised a test launcher for those, so I've added iMac DX and simulated as a factory, so it's very simple. If I've got a default, it's going to be my camera class. Otherwise, I'm going to have either my iMac DX or my simulated camera. DX and simulated right there. Again, same pattern for the state machine objects. We would create the SMO, register to the public events, and then start the process, the asynchronous process. On stop, we can destroy, and well, we can send a message exercising our API, and if there's a new image, well, we retrieve it, and then I've just got a picture control here to fit into the box. So here I'm ready to test, and iMac DX. Now I can confirm that my little light tells me that I'm being videotaped right now by my camera, and I'm gonna just hit the acquire. So you can see that we've got one image every 50 milliseconds, so it's a bit chunky, but that really tells you that it's actually working. And then if I go to simulated, And I acquire, there you go. So that comes from my buffer of images on disk. So we almost have all of our device separation layer complete now, calling instruments. I can probably just, for the sake of it, add my stage simulated, and my simulated class is extremely simple. It's just overriding the read position, where we do some maths to basically from the last time that we've called, we iterate based on the velocity, and that's that gets converted to counts and position. Just this little effect will make sure that we can retest again our XY stage, but this time by saying that we want to use a simulated instead of calling our method read position here that gets the coordinates, the instantaneous target. It's gonna capture it's gonna basically simulate a movement. So I'm gonna go to 50 and 50 and move, and you see that's the only difference. And so that allows me to quickly determine if my timeouts work correctly. Now this seems like a useful feature to test our application. I think at this point, before I go into integrating this into the microscope, what I'd like to do is go back to our UML diagram and discuss a bit about unit testability of this this architecture. So we're back with our UML diagram, which has been laid out a little bit differently just for convenience. I've had the camera simulated and XY stage simulated that we've introduced in the last segment, and we were talking about unit testability of a good hardware abstraction architecture. There are kind of three places where we want to create unit tests. Now, if you want to test within the hardware abstraction layer, you will create device-level unit test, meaning that a little bit like our test launcher for the camera, where we swap between camera simulated and a camera iMac DX, you can exercise directly unit tests using your camera simulated class and validate that the camera abstraction works correctly. Now, the next test is to do a driver level unit test for each of your modules that will be swapped for a camera simulated. And obviously these two tests can be combined once you do a system level test where you have a camera with actual hardware connected. So using your favorite unit test framework, either the NI unit test framework, JKI's VI tester, or Karaya, you can develop good, solid, reproducible unit tests here. And the third one is really an application level unit test, where once you've validated that each individual application separation layers were functioning properly through the use of different driver level or device level unit test, it makes sense also to produce an application level unit test where you will exercise your API from the microscope to the camera, from the microscope to the XY stage, or whatever other subsystems you might have. And this finally leads us to integrating our XY stage and our camera into our microscope. We had already seen that our public API was set to actually go into fetching the dependency for a camera and performing just logic, and the same thing for coordinates, where coordinates would do the same for the XY stage. And so we already have kind of a working application in a way. By integrating the public API of the camera and the XY stage, there's not much the microscope needs to do apart from just following basic instructions of or move to certain coordinates on the stage and then snap an image, return through the user event, whatever has been shown there. So As part of the framework of state machine objects, our microscope defines certain dependencies, which are a generic stage and a generic camera, and then we can override with our own factory or configuration-driven dependency injection. In this case, we have a hard-coded dependency injection instead of a dynamic lookup on disk, like a plugin architecture. This is where basically we'd enumerate our static dependencies and get the appropriate class from disk, casting it to the more generic, and then declaring that as a dependency of the microscope. Now, here, as I said, they're hard-coded, and the configuration file tells us which one we should look for. So we have the simulated camera, we have the simulated stage that we can interchange, and these I think I should probably add the files. This is where I would define my dependencies here. If I said not simulated, so we should get instantaneous movement, and simulated will get the simulated images. Now the simulated images will be fetched from my SEM images folder. I'll go to my subsystems for microscope, and as usual we have our test launcher, which we've asked our in-house designer to help me because I'm not that good with user interfaces, but basically he's helped me construct a very simple UI. All it does, and again you'll recognize the pattern, we create a microscope SMO, and then we look for microscope public events. This is actually an error. And then we start our microscope process. The starting of the process will launch all the dependencies. In this case, we have the camera and the XY stage dependencies. So after we're started, the dependencies will be ready to give us their public events. So we're going to monitor those public events as well. And then the rest is really about exercising our public API, just like we've done with the camera and the XY stage again. So here we have a capture image at certain coordinates, and we can capture the image immediately. So whenever there's a new position event from the XY stage, we will calculate on the picture control and do an overlay to just show where the stage position is at. We're initialized, and we're acquiring pictures. But there's something missing here. We really want to have our simulated movement. So I'm going to change my hardware abstraction dependencies here for a simulated XY stage. And we're still going to look at the SEM images. Going to relaunch this here. Once I'm initialized, I can move. Motion is in progress. As soon as I'll reach destination, I'll capture my image. And there we go. We've successfully created a microscope controller and ran our entire application using simulated data through the public API that we've designed beforehand. This concludes this presentation about hardware abstraction layers. In summary, we've seen that we can use JKI state machine objects to create a simple and solid hardware abstraction for an instrument with multiple components. The hardware abstraction layer provided us with many benefits. We successfully created a device-independent interface to physical hardware by dividing our software into an application separation layer and a device separation layer. We were able to create modular code that allowed us to swap hardware components seamlessly from a configuration file. We also showed that we could run simulated devices and test our workflow, making our software inherently unit testable. By taking time to design a generic public interface, we have prepared for future changes that will provide flexibility and minimize risk associated with instrumentation projects. Thank you for taking some of your precious time to watch my presentation. If you'd like to leave feedback about this presentation or discuss how JKI can help you be successful with your projects, please visit our website at jki.net.